Hey, how's it going? I'm going to be taking a look at homework 2, part 2a, which will explain and code the secant and Newton methods for finding the root of a function. We'll start with the secant method, and let me get out of here. Okay, so the secant method, as I was saying, is a root finding algorithm, and it uses secant lines to approximate the root of a function. So if we take a look at this picture here, we can kind of go through it. So the secant method, you have to have two initial guesses, x0 and x1 would be the guesses in this case. And you draw a line between the function values of those two x guesses. And then that line that you draw will cross the x-axis at a certain point. So the next step is to find the function value at this new x2 point, which is now your two guesses of x1 and x2. And then you draw a line between the function values of x1 and of x2. This new line will also cross the x-axis, in which case now you have x3 and x2, and you find function values for those. So x3 would be, or f of x3 would be down here. Then you draw a line between those 2 points, which if we look at it on this picture would go about there to there. That gets you another x point, in which you could find another x value, and you just continue until it approximately will converge upon this this root of the original function. So we can see the actual method for finding the zero here, and this is to calculate your next x point from your previous two. So to calculate your next guess, basically. Alright, so now let's take a look at coding this in Python. We're going to start with a few imports. We're going to import numpy, np. Then I'm going to import jax, and I will be using that for the Newton's method one, so we'll just have it there for now. Alright, there we go. Alright, so we'll start with defining the function secant, and it's going to take in our function. And as I was saying, we need to provide it with two initial guesses, so we'll provide it with x0 and x1. Then we don't want to get into a situation where we feed it a function that has no roots, and it could be infinitely searching for the roots to the function. So we'll want to give it a max iterations. I'll call that 50 for now, and I'll be playing around with that later in the program, so it's not a big deal. And then I'll set a tolerance level, and that's where we can just leave our loop if we arrive at our root. So I'll say that we want that to be essentially 0, so I'll set that times 1 times 10 to the negative 10th. Alright, so now we're going to want our function values first we're going to want a loop. So we're going to want to keep replacing our guesses with our new guesses that we get. So for I in range, and we'll say in range of the iterations, we're going to want our function values. So we want our f0, which is going to be equal to a function that we defined. I haven't defined it yet, but I'm going to be feeding this a function eventually. So, and that'll be f of 0 at x0, and then we're going to want an f1. That's going to be the function f at guess 1. And then we want to calculate our new x value. We'll call it x2. The equation calls it xn, and that's because it's going to go a lot more than 3 times. So you're going to end up, it's not really going to be x2. We'll just call it that in our code. So x2, what we'll think of as x2, is equal to x1 minus the function at x1 multiplied by x1 minus x0 over the function at x1 minus the function at x0. So now I just got to put that into Python. So x2 is equal to x1 x1 minus f1 times x1 minus x0, which are our two guesses, divided by f1 minus f0. And that is the equation that we have for the secant method to calculate our new x value. And now I set that tolerance value, so we want to say if, inside the loop, we want to say if, let's say the absolute value, because our could be going up or down, and if our new x value is less than our tolerance away from our last guess, we can just break the loop. Because we know we've reached the point we want to reach, and we're at the 0. So there we go. And now, we wouldn't really be doing anything if we just kept these same guesses, so we're going to have to modify our guesses. So we want our x0 to now be our x1, and then we want the x1, our second guess that we've had it, to be the new x that we just calculated, so x2. And then we're going to want to return x2 from our secant function. And this is going to be our root when our function converges. So return x2. Run that, looks good. Alright, so now we're going to define an actual function, so we'll just call this f of x. And I'll make it something simple, so something easy to see the roots. So we'll go x plus 3 times x minus 2. So our roots are just negative 3 and positive 2. Run that. Alright. So now we have a function. We have our secant function that's calculating our new x, and just running through until it hits the root. So let's check it out, see if it works. So I'm going to call on secant, and I want to feed it my function f, and some initial guesses. I'll just go 0 and 1. And look at that, so it gives the root of 2. Which we can clearly see as one of the roots of our function. Now I think there's a couple ways we could make this a little better. For example, when we break here, this means we've found the root. So, or found a root, because our problem with the secant method is that we can clearly see our function has 2 roots, but as soon as it arrives at one of the roots, it can't really go anywhere from there, so we can only find one root at a time. If we use different initial guesses, we might have found the other root, but it's just a matter of what your initial guess is. But now if we want to see, to verify that we found the root, I'm just going to make this root variable here, and we're going to set it equal to just success. And that's just telling me that I did reach a value where x2 minus x1 was less than our tolerance, so I found a root. And then if we reach the end of our loop and we did not ever get below our tolerance, I'll set root equal to did not converge. And then here at the end of our function, I'll just return x2 along with that root variable I just made. And this is kind of a cool feature that you can add in. That way when I run this, it'll tell me my root and it'll say success, so I know it converged. I can also throw in here the I variable, which is my loop variable, just to see how many iterations it took. So since my guesses were pretty close, it only took 7 iterations. So then if I come back here just to test out that root variable we made, and I say, let's say the iterations was 5, which is less than it took, and then I rerun this. Now, it has a value that is extremely close to 2, but it never actually hit below the tolerance reset, so it says did not converge. A way we might be able to see this better is if I make my initial guesses like 100, and I'll go 200. our root might be pretty far off. Yeah, so it's calculating the root of 10.8, but if you didn't have this root variable, you'd think it converged and you'd think that would be your root. So I like to throw this in just so we know and we can see whether it converged or not. Then obviously, if we change our iterations back to 50, even if our initial guesses are pretty far off, we're still going to hit. It just took 14 iterations, but we got to our root of 2. So this is the secant method, and now we're going to go on to a new method of finding a root, and that's going to be Newton's method. So define Newt. Now Newton's method is a little different. Let's take a look at that. So Newton's method only requires one initial guess, and it uses the derivative of the function to find the root. So let's find a picture down here. Okay, here's a good one. So basically you have your initial guess, and you find the derivative, then you find where this derivative crosses the x-axis, and then from here you find your function value at that point, so you'll get a new point, and you find the derivative at that point, and you just repeat. So then you'll find a new x value, derivative at that point, and you keep going. Looks like this might be a good demonstration to kind of show what I was just saying. So we'll find our derivative, next point, derivative again, and just continue, and eventually you'll converge upon where your root is at for the function. So it looks like this one took around 5 guesses. So like I was saying, this one only requires one initial guess, and then you solve for your next guess by doing we'll say x1 equals x0 minus the value of f of x0 divided by the value of the derivative of f of x0. So if we want to go back over to our Python, and we'll be doing the same thing. So Newton will feed it a function, we'll feed it a singular guess, and then we'll do the same thing, iterate with iterations and tolerance. And it's going to be a pretty similar code, so I'll come back here and copy this. We can get rid of this I was just messing around with that. Alright, so now same thing, we want our loop for I in the range of iterations. We want f0, and this time we also want our f prime of 0, so I'll go f prime is equal to jax dot gradient, which will just take our derivative of our function, and then fp0, which will be the value of our derivative at x0, so fp at x0. And now we just want to calculate the next point, so x1 is equal to x0 minus, I believe, the value of the function over the value of the derivative at that point. Yes. Okay, so f0 over fp0. And now we're going to want to do the same thing. We set our tolerance, so if our new point that we calculate changes by less than our tolerance, we know that our root solver found a root and we can break from our loop. If not, we rename our x0 as x1, and that's actually all we need since we only need one guess on this one. So we want our x0 to be the x1 we just calculated and to restart the loop and then check again. And I'll keep in that root variable just so we can see whether it converged or not. And this time we want to return x1. And I think that looks good. Let's run it and see what happens. I'm going to leave the same function, just a pretty simple one, so I know where the roots are, x plus 3 and x minus times x minus 2. So we'll call a new, feed a function f, and just for the first one I'll just make my initial guess 5. Well, let's see what I did. Oh. Oh wait, no, that should be fine. Did I run this? Jackson. Gradient requires real or complex value inputs. Oh, does this have to be a float? Okay, yeah. So I can't give the gradient a integer, it has to be a float. So I had to add that little decimal point there. Alright, so now if we want to take a look, we did indeed get our root. It's a value of 2. And I like having this root variable that told me our Newton's method function converged, and it found the root. And if I throw in the same thing, we can kind of mess around, see how many iterations it took, and that's all that I is telling us. So it took 5 iterations. If we make the initial guess a little worse, we'll make it 500. We can see that it takes 11 iterations. And I'll show the same thing where if I come back and say only do 5 iterations, and this one clearly took 11, it just told me. It'll tell me it did not converge, so I know that this is not an actual root of the function, and that I need to fix something. The something to fix here would just be putting my iterations back to 50. And now I have the root again. So that's that. And yeah, so let's take a look. Yeah, I think we explained and coded both the secant and Newton methods for finding the root in Python. So there we go. Thank you.